Good morning. Today's lesson is on length of daylight in Houston and Philadelphia. It's part A and B of SAS 4. There will be an assignment in the Google Classroom for you. All right, let's start our day off with good things. Good thing I had a visit yesterday with some friends of mine that I met through my YouTube channel. We've known them for 3 years. First time we got together, they're from Murfreesboro, Tennessee, which is not far from where we used to be from, and it's amazing we never met them before we left that part of the United States. Anyway, it was a really good visit. Probably be a post on my my other YouTube channel about it. But anyway, that was a good thing for me. Please be sure to share your good things with me. I love to share them. I know that my tennis team did fairly well during the tournament. Our girls doubles placed 5th out of 32 teams in this tournament. So, and we got some good things going on. Just want to let you know things are going well. You should let me know too so I can share with the rest of the classes. All right, so let's start this off with this. Let's locate Houston and Philadelphia. In terms of latitude, it says in longitude, but I don't think it's that important on the map. And which city would you expect to? Well, first of all, let's see. Philadelphia is right around 40 degrees latitude. Houston's right around 30 degrees latitude. There's 10 degrees between them, okay? So which one do you think would be the warmest during the summer? Well, most of you are going to say Houston, of course. All right. And which one is going to have the longest day during the summer? And my experience in this class has led me to believe that every time someone gets asked this question, they say that Houston is going to have longer days during the summer. All right. Then which one do you think is going to be coldest during the winter? We would obviously say Philadelphia because they get snow and Houston rarely does. Which one has the longest days during the winter? We would probably say that Houston does. We'll see. We'll take a look at it at length, and that's what we're going to do. You may notice that during the winter, the days are shorter, and during the summer, the days are longer. How much longer are days during the summer, and does the length of the summer days change depending on the latitude of the place? I think we can pretty much say that that's true on all accounts. You're going to investigate these questions using data from 4 different cities at 4 different latitudes. Houston at 30, Philadelphia at 40, Winnipeg at 50, and then Porto Alegre in Brazil, which is 30 degrees south. The rest of them are north of the equator. Brazil is obviously south of the equator. And we'll look at that one in section SAS 5. The data in the tables for this activity describe the length of daylight for the year 2009. The data table is based on 2 assumptions. Length of daylight is defined as the amount of elapsed time between sunrise and sunset. And because 2009 is not a leap year, there are only 365 days in a year. So which city would you expect to have more daylight during the summer, Houston or Philadelphia? People are going to say Houston almost every time. What do you think so? Because it's warmer. Just seems to be a lot brighter sun down there and everything. Anyway, let's move on. So let's look at this at length. We've got a chart here showing by day number how many minutes each day has of daylight. Of course, that daylight on day 1, on January 1st, 617 minutes from the time the sun comes up till the sun goes down. And that's what we're doing. We're going to make this graph easier. We're going to make a scatter plot. January 1st is day 1. December 31st is day 365. And we'll graph the length of daylight in terms of minutes. So we'll look at it here's our chart. Day number here, all the way to 365. You can't see it because it only goes to 360. And this is all the way to 1,000. And believe it or not, there's only 1,440 minutes in a day. So there you go. So we're going to chart all these minutes. We're going to put 617 right here for day 1, 648 for day 32, and so on. And they all come out and look like a nice little bell curve, don't they? All right, so we're going to actually enter the data into a stat list of your TI-84 graphing calculator using stat edit. So we'll go stat here, and then edit up here. We can just probably hit enter. And then we're going to use the day number for L1 and the minutes of daylight for L2, okay? So it'll come out like that, all right? And when we chart it, and we actually graph it, zoom 9 will give us the actually what it'll look like. Sketch your graph and describe your axis. It'll look like this. Of course, you're going to have to turn your stat plot on for this to work. And to do that, you're going to hit second y equals and then turn it on, all right? Your calculator has the ability to generate a sinusoidal regression model. We'll record the equation and round values to the nearest hundredth. If you go into your calculator, I'm going to back up. You're going to go stat and then arrow over to calc and then arrow down so you get to sine regression. Okay? We're going to record the equation and round the values to the nearest hundredth in the summary table provided. I've got a portion of the summary table provided here for us to go over. We're going to factor the value b after we get this sinusoidal function. And what we'll do is this little part in this quantity, bx minus c, we're going to calculate the b by dividing out the b from both the x and the c. Well, there's a b times x, so it'll be b times x minus c over b. And we'll include this form in the equation as well. Okay? So the regression rule is 113.26 sine times 0.017x minus 132 plus 727.37. And factored out, it looks like this. And we're going to put it into our regression model, our little summary table for the daylight, length of daylight. All right? Now, we're going to graph the model over the scatter plot here and see if the curve matches it, okay? And lo and behold, it does. It follows right over that curve, all right? So we'll connect the points of the scatter plot with a curve on our paper part, and I'm going to want you to do this on your piece of paper that you're going to have. And it'll look like this. You're going to have it just a line to each point. And this doesn't have to be perfect. You just have to understand that what it looks like is it is a curve, okay? So we're going to use a calculator to determine the maximum and minimum values. And the way you do that is you're going to go and after your values are in there, I'm maybe able to do this with my calculator. I think I have it in. Yes, I do. All right. So I have both Houston and Philadelphia in there. But I want you to see something. If you go second table, okay, that's not going to work. Second quit. Graph, that graph is not going to show unless you zoom 9. There's my curve. And I haven't put y equals in there. I can put it in there if I want to see what it looks like. It will be, let me back this up one so I can see. Oh, I can see it right there. All right. I'm going to put it in there. See what it looks like. There we go. Mm-hmm. Yeah, I am. You're like kind of getting in my video. Get out of my video.
They're going to see it. Wait, they're going to see it?
Evaristo, you realize I can edit all that crappy hair out of there.
All right.
I'll Photoshop the hair off your head. You'll be bald.
I'll lick on top of your head.
All right. Use your calculator to get out of here, guys. Come on. I can't do this if you're bothering me. Use your calculator to determine the maximum and minimum values for the length of daylight by day in Houston. You're going to record these ordered pairs here in the maximum and minimum section on your summary table. To which dates these values correspond, you'll actually put that in there. So in the maximum value, the ordered pair 172 and 841 represents the maximum length of daylight. Day 172 is June 21st, the summer solstice. It has a maximum of 841 minutes, 14 hours and 1 minute of daylight. And that's all in the summary chart. The minimum value, the ordered pair is 359, 614. 359 represents December 25th, close to the winter solstice of December 21st, and has a minimum of 614 minutes, 10 hours and 14 minutes of daylight. So we're going to go to Philadelphia now. We got a chart for Philadelphia, and we want to make a scatter plot of length of daylight the same way we did for Houston. And we left Houston on there, so let's look what the length of daylight plots will look like for Philadelphia. Notice that these are not the same curve. They're in the same period, but they're not the same curve. So we're going to use the stat edit function and put those numbers in there. We're going to put them in L3 instead of L2 because Houston already has L2. And we're going to use the calculator to make a scatter plot. And of course, you have to turn your scatter plot on. Second, y equals, and then make sure your plot 1 is on and plot 2 is on. Okay? Notice it plots over the existing Houston. There's your plot with the numbers going over it, just like the one we did on paper. All right, we're going to use a calculator to generate a sinusoidal regression model for this one too. We'll factor out the b just like we did the last time. The regression rule is 168.44 sine. And notice this quantity and this addition is almost the same as the last form. So we'll put those into the summary form, both parts, even the one that has this b factored out. graph the model over the scatter plot, and guess what? It follows it perfectly. Notice the curves are in the same period. The bottom is at the same point as the Houston curve, and the top is at the same point as the Houston curve. But there's a little bit further down on the Philadelphia, a little bit higher up on the Philadelphia than the Houston. Okay, so we're going to draw points on the scatter plot that we created on the paper, and as you can see, it makes another curve just like the one we did in the Google Classroom or in the TI-84 Plus. All right, we're going to use a calculator to determine the minimum and maximum values in Philadelphia, and we'll record these in the summary table. So the maximum is 172,894. Day 172 is June 21st, which happens to be the summer solstice. And the greatest amount of daylight is the longest day, 894 minutes and 14 hours and 54 minutes. And we put that into our summary chart. The minimum values are 361 and 558. It represents the minimum length of daylight. December 27th is day 361. It's very close to the winter solstice and has the least amount of daylight, shortest day, which is 558 minutes or 9 hours and 18 minutes. Now, how does the maximum length daylight for Philadelphia compare to the maximum length of daylight for Houston? If you look at them, the maximum daylight for Houston is only 14 hours and 1 minute, but for Philadelphia, it's 14 hours and 54 minutes. So there's 53 minutes longer in Philadelphia of daylight on the longest day. And look at the minimum. The minimum for Houston is actually more than the minimum for Philadelphia. So you see it flips, and that's what the curve looks like too. The curve helps. The maximum length of daylight for Philadelphia is greater than the maximum length of daylight for Houston. In other words, Philadelphia's longest day is longer than Houston's longest day. And how does your answer for question 7 compare to the prediction? We predicted possibly that Philadelphia's days were shorter in the wintertime. And that's not true. They're actually, they are shorter in the wintertime, but we also predicted them to be shorter in the summertime. They're not. They're actually longer in the summertime. We'll look at it again. Intersection points are given. 77, 725, and 267, 725. The intersection points are actually, it is the spring equinox and the fall equinox. These are the days that actually have Houston and Philadelphia have the same length of daylight on those days. The beginning of spring and the beginning of fall are the days that we actually have the same length of daylight. All right. When is there more daylight in Houston than in Philadelphia? And is it what you expected? Why or not? There's actually more daylight during the winter months in Houston than, so in between September 24th and March 18th. This is what is expected since the vertical lines, length of time of Houston graph are above the corresponding values Philadelphia graph during the first and last quarters of the calendar year. And less daylight in Houston than in Philadelphia during the summer months between March 18th and September 24th. That's what is expected since the vertical lines length of time on the Houston graph are below the corresponding values of the Philadelphia graph during the first and last quarters of the calendar year. And that's what we discussed when we looked at those curves put together on the graph. All right, what's the difference in latitude between Houston and Philadelphia? 10 degrees. Philadelphia is 10 degrees higher up than Houston. What about the difference between Philadelphia and Winnipeg? Foreshadowing to the next lesson. It's also 10 degrees, and we should probably expect a little difference in there, the length of daylight between Winnipeg and Philadelphia. But I want you to look at this. In a launch, there's common misconceptions about solar and terrestrial physics. Solar means sun, terrestrial means earth. People often think that the earth is closest to the sun in the summertime, or it is warmer in the summer because the earth is closer to the sun. That's actually false. It is most common misconception about a relationship between the sun and the earth, and is unfortunately perpetuated by lousy diagrams in most school textbooks. When someone says we're close to the sun in the summertime, do you ever remind them that while it may be summer here in the northern hemisphere, it's actually wintertime in the southern hemisphere? And 6 months from now, the season in Earth's position will be reversed, and we'll have winter here and it'll be summer down in the southern hemisphere. Change of seasons is mainly the result of the tilt of the Earth's invisible spin axis, which is inclined 23.5 degrees in comparison to the axis of the sun. Now, sometimes Earth's axis is tilted toward the sun, sometimes away from it, somewhere in between for the rest of the year. It's this tilt combined with the motion of the Earth around the sun that causes more or less light to fall on one hemisphere or the other during each of the seasons. This means that the amount of sunlight falling directly on a parcel of Earth changes throughout the year. It also means that days get longer or shorter, causing the sun to warm part of the Earth for longer or shorter periods of each day. So that's it for the lesson. Go back in the Google Classroom. Be sure to do that assignment that's in there. I appreciate your time. In the meantime, be blessed and be a blessing.